Okay, we're going to talk about neural nets. And so the basic idea behind neural nets, and we talked about earlier how using high-dimensional embeddings in kernels, you can turn linear methods into nonlinear methods. Neural nets, instead of doing fixed high-dimensional embeddings, we're going to compose linear functions and simple nonlinear functions into neural nets, which will give us nonlinear predictors. So that's going to be the neural net approach. And recently, of course, there's been a ton of developments within the neural net realm. Basically, the driving force behind the expanded use of neural nets is the recent advances in the optimization tools for neural nets. And as we'll see, neural nets before were, because they're non-convex, they produce non-convex optimization problems, people were sort of hesitant to dive into that because optimization in the convex domain has all sorts of guarantees. We know a lot about it, and it took some time to get sort of foolproof techniques for optimizing non-convex optimization problems. So that's but recently, these optimization tools based on stochastic gradient descent have been proven to work in a wide variety of neural net architectures. So we'll talk about that, but first let's just talk about the basic feed-forward neural net and some of these ideas here. So, okay, so the basic idea is that, of course, neural nets. Oops, let's not use purple. Let's use black. So neural nets use composition. Composition to build from simple functions, more complex ones. So when we compose two functions, that just means applying one after the other to the output of the other. To build nonlinear functions. So what does that look like? So one way we can draw a neural net is using our compute graph. So in the predict step, we had, for example, a linear compute graph. Sometimes it's computation graph or computational graphs. So I'll go somewhere meet it in the middle. Computation graphs. The basic idea there was that you had your input, x, and let's just draw it out down to xp. This is for the predict method. X1 to xp, right? And you also had your weights, right? So you also have your weight for the compute graph. So we have W, say, let's call it betas, beta 1 down to beta p, and then these got multiplied together. So we'll do just multiplication with a dot. Right. These get multiplied together, and then all of these get combined into an addition step. Right? And then we have beta naught also comes in, and so we'll just draw a 1 here, and we can just think of the 1 as an additional input. These get multiplied, and then this also gets added together, and there's several of these. Right, so the compute graph, computation graph, the basic idea is that you have your input x's. I've written them as separate variables, so each of these are scalars now. And then you have these betas and your beta naught, your intercept term. These all get multiplied together and then they get added. And of course you can write this more succinctly as your x and your beta. You apply a matrix multiply to this. Right? That can be written more succinctly, of course. And then you could add in the intercept there. So that's your basic idea for a linear predictor. So linear predictor computation graph. Right. So now let's think about neural nets. The basic idea is that instead of taking just making your output a linear function of your input, we're going to think of creating new input using another linear predict and then some non-convex what we call an activation function. Right. So let's do that. So we take our input x1 down to xp, and then we apply our. So I'm going to write this more succinctly as we're going to take our input and we're going to combine all of these. Right? So let's take all of our inputs and just apply a linear predict transformation to this, including the intercept. Right? Okay. And we'll just call this this operation here that happens. We'll call it sigma of beta. Actually, I'm going to use W1 transpose X. Here, let's draw this whole thing out. W1 transpose X plus, let's call it W10. Right? So we're going to create a linear function of the input, our linear function of the input, using our new variables. These are trainable variables, W1 and W10. Right? And then this here is an activation function. So and then, yeah. So what we're going to do with this is now we have some output function which is nonlinear, possibly, because we're going to use a fixed activation function, the sigma function here. So let's just call this an operation. And to make it clear that it's an operation, we'll put a dot here to indicate that that's an input variable. Right? Now we can do this multiple times, right? So we can create other functions here by doing W2 transpose, some other weight, times your input plus W2 naught. Right? We can call this another operation, and then so on until we're happy with the number that we've done. So let's call W sub capital H this plus W capital H naught. Right? Okay. And so we're just going to, as usual, represent this the directions in this computation graph using arrows. And then, now that we have these nonlinear functions, possibly nonlinear functions of the input, we're going to use them in a further linear as a further linear function. Right? So we're going to create betas, have other beta trainable variables, which we're just going to do. This is going to get the operation, which is the sum over, it's just going to be beta transpose whatever the input here plus beta naught. Okay, and this becomes our predict method. This is our predict method. And it has trainable variables with variables wj, wj naught, beta, and beta naught. Right? So these are vectors in Rp, p, wj, and j goes from 1 up to capital H. And beta is in R capital H, and beta naught, this is in R, and this wj naught is also in R. Right? So we have these trainable variables for this function. If we want to write it out in math and not in the computation graph, then the way it would look is our f of x is equal to beta transpose this sigma, and I'll describe the sigma in a little bit, capital W transpose x plus W naught plus beta naught, where in this case W is in is P by capital H. So each column of W is a different W sub j. So this W sub j are the columns of capital W. And W naught is in Rp. So it's of size P. Right? So this is a more succinct way to write it out in math. Oftentimes you'll see a feed-forward neural net drawn in this sort of dense representation. A more succinct way to draw this compute graph is just to say that you have input x coming in, and then you have W and W naught, and then it gets sigma of this W transpose. We could write it x plus W naught. Gets then the output of this, and then we introduce beta and beta naught. This gives us f of x. Right. And so x first undergoes one operation, which is nonlinear, and possibly nonlinear, and then it undergoes the output of that undergoes a linear transfer operation. So the sigma, this is called the activation function. Right. And the activation function, there's a number of possibilities, but it's typically nonlinear, possibly nonlinear. It could just be the identity, or it could be the identity. In which case you would maintain linearity. So for example, sigma of z could be equal to the sigmoid function, sigmoid activation. This is sort of a classical this is a classical activation function. And the way this looks is asymptotically it starts at -1. It goes through 0 at 0. This is 0. And then it asymptotes back to 1. And so this is a smooth surrogate. It starts at 0 and then asymptotes to 1, and it hits 0 at 0. Or sorry, 1/2 at 0. Sorry, I got it mixed up with the tanh. Doesn't really change all that much. The basic idea is that this is a smooth surrogate for the indicator that z exceeds 0. Now, why would we want it to be smooth? Well, when we go to train this, we're going to want to take derivatives or subgradients, at least subgradients, of this activation function because we're going to use stochastic gradient descent. And if we want to make changes, if we want to make incremental changes in the w, then we're going to need gradients with respect to the w, so we're going to need to pass our gradients through the activation function. And so if we have at least something that is an activation function which is continuous, then we could possibly take subgradients of the activation function and plug those in. So with the sigmoid function, because it's smooth, we can take its derivatives. We actually use closed form versions of its derivatives to be able to do stochastic gradient descent in our trainable variables. Okay, so these w's, the common nomenclature, the tensors that come out of this are typically called hidden units, or maybe we'll just call the operations themselves hidden units. So this is hidden units. And this whole thing combined is called a layer. So this entire operation is called a layer. And then the output will go from x to, so we go from x to the first layer and then to the output for this simple single hidden unit, hidden layer neural net. So one way that you can think about this is we're iteratively constructing features for the linear layer, but instead of fixed features like we do with high-dimensional embeddings, we're going to use trainable features because this W matrix is going to be learned as well. So we typically call this representation learning because we're actually learning the features and not just using fixed high-dimensional embeddings or fixed features. So let's think about how we can do this. So the hidden units, the basic idea behind the hidden units is that we have a weight vector, capital W1 down to W capital H. This is used to construct feature which I'll call little h1, which is equal to the sigmoid applied to W1 transpose X, and then we'll just add the intercept here, 1, 0. And then this also constructs a feature, so all of these will construct separate features, H sub capital H, which is equal to sigma of W capital H transpose X plus W capital H 0. Okay. So we're constructing all of these features, and they're all scalars, right? And so, if we were to fix these W's, then it would just be as if we constructed separate features which are possibly nonlinear functions of the input. So this is, if we fixed our w's, say we chose them randomly. This is actually something that you can do, is use random weights and then apply an activation function and then use this as your new features. And random features are used all the time in machine learning, so this isn't that uncommon. But what we're going to do is we're also going to allow these w's to move and to shift so that our constructed features are actually learned and not just fixed. And so this is often called representation learning. Okay, so how can we think about what neural nets can then approximate? Because now we get a much more rich function class because we're allowing these w's to be trainable. How also can using an activation function give us something that looks nonlinear and nonlinear decision boundaries? So for example, if we think about, this is actually non-trivial. If we think about the level sets, so let's think about a level set of the sigmoid function applied to some W1 transpose X plus this W1 0. Right? If we think about this, the input to this activation function, this is linear, right? And the sigmoid function that we're using, say the usual sigmoid function, this is a monotonic function, and so its level sets are going to be linear as well, right? So you can think about maybe the point at which it crosses 1/2. The level set for 1/2 is here, and then level sets are going to be, say, here. Maybe this is for 2/3, and then it's going to be here. If you think of this as a topographical map, then you have the largest amount of change, the largest elevation change, as being around this 1/2, because that's just what the sigmoid function looks like. It has the largest elevation change around 1/2, when its level is 1/2. And then you have that it has much smaller changes as you get away from this 1/2 decision boundary, or the 1/2 level set. And so if you think about a different activation function, it might look more like something more like this. This could be 1/2. Because of this nonlinearity, then when we add these two functions together, say we just are going to, say, average these functions, so our beta has the effect of just averaging these two. Say beta 1 is equal to 1/2 and beta 2 is equal to 1/2, and there's just two hidden units. So this is sigmoid of W2 transpose X plus W2 0. When you add these two together, then you end up getting something that actually has nonlinear level sets. This is sort of the point. So maybe it produces something that looks like this. Right. And this is sort of not exactly obvious that this would happen, but it's because you don't have just a linear sigmoid function. You have it so that these level sets have different spacing between one another. Sort of as an extreme example, let's think about a sigmoid function which is not smooth or continuous. It's just the of z is just equal to the indicator that z exceeds 1/2, for example. So this is sort of the non-continuous z exceeds 0. This is sort of the non-continuous version of the sigmoid function. So in this case, the level sets, it's just going to be, let's think about this again. In this case, we still will have the same decision boundary, but over here it's 1, and over here it's 0, for example. And then this one, if we think about it, then here we're going to have it be 1, and down here it'll be 0, for example. So then when we add these two together, then we get something that looks like the following. We have a function which looks like the following, where these 2 points overlap. So that's going to be something that looks like, right? Where these 2 overlap, the value is 2 here. Where they do not quite overlap, so something like this, the value is 1. And then here, the value is 0. Right? And so you see that you can get some very nonlinear functions just by adding together 2 of these hidden units, where the activation function is just the indicator function. Right? So this is how we can think about the construction of nonlinear functions from linear functions in a neural net, or in a neural net, using just an activation function. Okay, so so next time we'll talk about how to train neural nets. This is just predict, right? This is just how you would do the predict if you were given these fixed trainable variables. But how exactly are we going to learn these trainable variables? And then we'll talk later about optimizing neural nets and optimization for deep learning.